Welcome to this video lesson in which we will begin our discussion about energy. So what I want to do today is tell you what energy is and also introduce the various units that are important for us as we work with energy in our everyday lives. So let's begin with answering the question as to what is energy. Some of you may be using an app on your phone that counts calories. For example, this is an app that I have on my phone, and I use it to record my daily walking exercise and things like that. So what this app is telling me is that I walked 1.67 miles in some time, and I have something known as 186 calories that are being shown here. So what is this number, or what is this quantity? Here's another thing to look at. You did an experiment where you blew up a balloon many times, or probably blew up many different balloons, and in that process you realized that you might have started sweating, maybe, right? And you had to take a break between blowing up balloons. So what is going on here? Well, calories is a unit that is expressing how much work or how much energy we are using up. Yeah? And in this example here, from my calorie counting app, what it is counting is how many calories of energy my body is using in order for me to able to perform this walking function, right? So let's look at this idea of energy a little bit more. Here are two examples. You have cell phones, and you have automobiles that may be gas powered or battery powered, and we know that every night you need to charge your cell phone so you can use it the next day, because the battery requires some charging process to make it work, right? Similarly, if you have a gas powered car, periodically you have to fill in gas so that that gas can be burnt in order for you to drive your car from distance from your home to work and back, for example. So what is going on here? Well, the battery in the cell phone and the gas in the car, or if you have an electric car, the battery in the car is providing the energy for the car to do something useful, right? So the definition of energy is that it is the capacity to do work. Okay? So now we have introduced a new term here, energy, and then we've gone on to something called work. So energy is being used to do work, right? So what is this idea of work? In science and engineering, we measure energy through this idea of work, and I'll come to that in a moment. But before that, I wanted to tell you exactly what a calorie is. So a calorie is defined as the energy required to heat 1 gram of water through a temperature of 1 degree centigrade. Okay, so that means you put a pot of water on your cooking stove. In order for that water to heat up by 1 degree centigrade, you would have had to provide for each gram of water a calorie of energy. Another reference point here is that typically when we walk at about 3.5 miles per hour, you walk a mile, you're burning about 100 calories. 1 gallon of gasoline in your car has 31,500 calories. Okay? So now that we know that energy is required to do work, so it tells us that energy and work are related quantities. So let's go and explore what work actually means. Right? Now, in our everyday language, we often use the term, I worked hard today, for example. So if you had an exam coming up, you would probably be spending many hours working towards preparing for the exam. Right? So the definition of work is that it is the effort or energy put into an activity. And in science and engineering, we can measure different types of work, and one of the most common types of work is called mechanical work, and that is measured as W, which is work, is given by the product of something called F times the distance d. And here F is called the force. It's measured in a quantity called newtons, and we are going to talk about that in a moment. Okay. Now the important thing to remember is that the units of work are the same as that of energy. Okay. So for example, if you represent energy by calories, then you can represent work done also by calories. Now what is this force? And we'll talk about that on the next slide, but just to kind of give you a sense of where we're going, think about your balloon experiment, especially when you filled up the balloon and you released it, right? So the balloon moved a certain distance after you released it. How did it move? So obviously you expended some energy in filling up the balloon, and you blew air into it, and the air expanded the elastic of the balloon. And then when you release the balloon, the elastic of the balloon kind of compressed the air out of the balloon, and that forced the balloon to move in a direction opposite to where the air was coming out from. Right? And so it turns out that what is happening here is that the exhaust of the balloon is pushing the balloon to move in the opposite direction, and so that is the force that is appearing here. The force is a pushing or pulling agent. Okay, and so what we see from this is that the energy and work are connected to this pushing or pulling agent, which is the force. So what is the force? Well, the definition of force is that it's a pushing or pulling agent, and this is a qualitative form of it. What we would like is some engineering form that allows us to measure the force. And before we get to that, let's look at some examples of force that we experience in our everyday life. Here are three cases. When you're running or jogging, or when you're on a bicycle, or you're on a skateboard, or whatever other form of motion you might be used to, there's always a chance that you can fall to the ground. Why is that? Well, because there's gravity, and that's exerting a downward force on you at all times. Right? Now, as you're viewing this lecture, you're probably sitting on a chair, and you can feel that the chair is exerting an upward force on you, because if that was not the case, you would actually fall down to the ground. So here the chair is acting an upward force on you. Similarly, when you sit in the car and you start from stop, your body tends to feel a force from the chair, and that's because of the fact that the chair or the car is exerting a force on you. Okay? And so this force, as you will see, is either kind of pushing on you or pulling on you. And so that's what we mean by a pushing or pulling agent, right? Let's look at the force that acts on a plane that makes it fly. It turns out that there are four types of forces that make it fly. Right? The weight of the plane is, of course, pushing it down. That means gravity is pulling it down, right? So if I just did not start the engine of the plane, and for example, think about a toy plane. You just instead of giving it some forward motion, you just release it without any motion. It's just going to fall to the ground, right? Because of weight. Now if you give it forward motion, you're providing something called thrust, so that makes the plane move forward. Now in real planes, there are two other forces, and one is called lift, which is basically related to the shape of the wings. And the shape of the wings of a plane are very carefully designed so that when it travels through air, there is a net upward force acting on it, so that it keeps the plane basically flying, right? And then finally there is friction force acting on due to the air moving across the surface of the plane parts, and that is known as drag, and this tends to slow the plane down. So these are four different forces that are acting on a plane to keep it in motion, right? It's a competition between pulling and pushing, and basically a push and pull, and depending on which wins out, the plane is either flying or it is falling to the ground. Now in terms of engineering, in the case of the plane, for example, if you're thinking about simple linear motion of the plane, the force on the plane is given by F equals m times a. M here is the mass in kgs of the plane, and a is a quantity known as acceleration, and it is measured in units of meters per second square. Now the common units of force is called 1 Newton. So 1 Newton is basically 1 kg multiplied by meter per second square. So it's kg meter per second square. That's the SI dimensions, the SI units for the force, and in common notation it's known as 1 Newton. Okay, so we introduced the acceleration in the previous slide. So let's think about what acceleration is. Shown here is a list of the top 10 cars in terms of their speed, or in terms of how fast they achieve the speed of 60 miles per hour starting from stop, that is starting from 0 miles per hour. So you can see, for example, a Porsche 918 Spider does it in 2.1 seconds. A Porsche 911 GTR does it in 2.5 seconds. A Tesla Model S does it in 2.28 seconds. So what is that telling us? It is telling us that the speed of the car in going from 0 to 60 miles per hour changes in 2.1 seconds. So now we can measure something known as the rate of change of the speed, which is the speed change, in this case 60 minus 0, divided by the time it takes, that means 2.1 seconds, right? So this quantity, which is a change in speed over change in time, is known as acceleration. So the definition of acceleration is that it is the rate of change of speed or velocity. Okay. In engineering, this acceleration, this should be acceleration here, it's defined as a equals change in speed by time, and this is a formula that you will find in engineering textbooks. A equals dv over dt. dv here designates the change in speed or change in velocity, and dt here designates the change in time. So in this case, the change in speed or velocity is 60 minus 0, and the change in time here is 2.1 seconds. The SI units of acceleration are meters per second square. Okay. So one thing to remember here is that in our definition of force, what I have not mentioned is that force has a magnitude and a direction. Okay, and it is something known as a vector quantity. Vector quantities are engineering quantities that have both magnitude and direction. For example, the weight of a man or a weight of a woman, or rather the mass of a person, does not have any direction. Okay. On the other hand, acceleration and velocity are also vector quantities because they have magnitude and direction. And we will not worry about that too much in this class, but it's something to think about as you read up more on quantities like force and acceleration. Okay, so now let's turn to the idea of units here, especially in the context of energy. Right? Remember, we introduced the fundamental units in our topic of measurements, and three of those fundamental units were distance, x in meters, time in seconds, and mass in kilograms. So now let's take these three units and basically combine them in different ways. So here's the first one here, where we have defined velocity, which is the rate of change of distance with time, and you can see it's a ratio of x divided by t, and so you get meters per second as the units here. You may want to use uppercase M so that you distinguish between mass and meters, but remember, we have a formula here and we have the units for the formula down here. Okay. Now let's look at acceleration. Acceleration, as we said, was the rate of change of the velocity with time. So that means I take my velocity and I divide it by time, I get meter per second square. Force was mass times acceleration. So now I take my acceleration and I multiply it by the mass, which is in kilograms, so I get kg meter per second square, and this unit is known as 1 Newton. Work or energy is now force times distance, which is this quantity here, and now if I multiply my force in kg meter per second square by distance in meters, I get kg meter square per second square. and this unit is known as 1 joule. And finally we come to a quantity called power, and I'll let you understand what's going on here. So what I've written down here is the formula for power. It says here that it's the change in energy per time, right? So it's the rate of change of energy per time, and now I take my energy units and I divide it by time, which is a second, and so I get kg meter square per second cube, and this is known as 1 watt. Okay, so with that, let me just give you some common terms and common forms of energy units. We already introduced the calorie. It turns out that the SI units of energy is the joule, and the calorie is 4.18 joules. And remember, the calorie is the energy to heat 1 gram of water by 1 degree centigrade. The other unit that you will come across, especially when you do your design experiment that I will talk about shortly, is the BTU, or the British thermal unit. So 1 BTU is 1055 joules, and it is the energy to raise 1 pound of water by 1 degree Fahrenheit. Finally, I also want you to know what the kilowatt hour is. So 1 kilowatt hour is 3,600,000 joules. So 3.6 into 10 to the power 6 joules. Okay. So so that is 3.6 into, yeah, so that's 3.6 into 10 to the power 5 joules rather. So 3.6 million joules. And a kilowatt hour is 1000 watts of energy applied for power, right? So remember, watts is power, and that has been running for 1 hour. Okay, so that is 3600 seconds, and this is again a unit that we are going to be using when you do your design experiment or do your design activity later on. Okay, so let's move on to this final issue here of dimensional analysis. Okay. Some of you may have heard this term in your high school math classes. Dimensional analysis is the process of comparing engineering quantities in terms of their fundamental dimensions. Okay. And the reason it's important is that it allows engineering quantities to be expressed in terms of other engineering quantities. Okay, so this is something that is going to be very important for you as you move forward. Okay. So here's an example. The example here is asking you to find a formula for power in terms of velocity. Okay, so let's think about what velocity is. We know that velocity has units of meters per second. In terms of dimensions, it has length raised to power 1 and time raised to power minus 1. Similarly, if I look at power, it's kg meter square per second square. In terms of dimensions, it means that it is mass raised to power 1, it is distance raised to the power 2, and it is time raised to power minus 3, m L square t minus 3. So now my question here is to find a formula for power in terms of velocity. Since I know that velocity is meters per second, I look at how I can fit that into my power expression. I see that I can write it down as v square, which gives me meter square per second square, and I'm left with 1 second unit raised to power minus 1. And so my power in terms of velocity formula now becomes power equals mass times v square divided by time, right? So that would be an equation that relates power to velocity. So this is how you can do dimensional analysis to relate one quantity to another with some restrictions, and that is something that comes from practicing how to do these analysis. Okay. So as an example, do these two exercises here. Find a formula for force in terms of velocity, and then find a formula for the energy in terms of velocity. Okay. So the next thing is to also understand scales and prefixes, and for that I want you to really think about, for example, the range in scales that engineers are used to working with. So on the right side here are things that are made by engineers. I already mentioned to you the micro electromechanical system, which is of the order of microns, What is shown here is the head of a nail or a pin, and this is of the order of about a centimeter. And you go down the scale, you'll see that viruses are of the order of 100 nanometers. So 1 nanometer is 10 to the power minus 9 meters. Similarly, 1 micron or 1 micrometer is 10 to the power minus 6 meters, and that is what a microelectromechanical system length scale is. So what we need to do is we need to become used to understanding how to use these prefixes, for example a nano and a micro. And so here's a table that you should start getting used to, because you will need to be able to use these. You should be able to use these prefixes either in terms of multiples or in terms of fractions. So the important multiples here, for example, are kilo, mega, and giga. So kilo means it's multiplied by 10 to the power 3, mega means it's multiplied by 10 to the power 6, and giga is 10 to the power 9. Similarly, for fractions, what you should be used to are centi, milli, micro, and nano. So centi is 10 to the power minus 2, milli is 10 to the power minus 3, micro is 10 to the power minus 6, and nano is 10 to the power minus 9. So this table is something that you want to be familiar with, because you will see often engineering quantities are represented by quantities that have either the fraction or a multiple as a prefix to them. For example, 1 kilometer is 10 to the power 3 meters based on a prefix of 10 to the power 3, and as just said, 1 micrometer is 10 to the power minus 6 meters based on our fraction here. Okay, so to wrap up, please make sure to go through the additional resources in terms of lecture slides that support this lesson, and you will be doing a design activity that will be coming up at the end of part 2 of the energy discussion that is to follow shortly. Thank you.